where it's actually hollow, right, is going to be equal to half of say, let's call this E naught, right? Half of E naught is sigma over the epsilon naught, right? Okay. And the point of this problem is to show that, remember, I don't know if you remember this from a while back, when we have to calculate the energy to actually form this shell, right? And I argue by looking at the work done that to assemble it, and you find that the force that you need to counteract, there's a force here on the shell, right? And that is actually given by half of the electric field, half of E naught and sigma, okay, right? This actually comes from that. Okay, so right. So when you did this problem, right, you actually have this as a sum of the conducting sphere plus a small little patch with a minus sigma, right? So the electric field of the patch itself cannot act on itself. So that's why we have that, right? The force only comes from the rest of the sphere. Okay, so that's just a small little point if we continue on from yesterday. So today we're going to talk about inductors and capacitance. Okay, so this is chapter 3 on Purcell. So before I do that, I recall that when you have a surface charge sigma, okay, this is also what we did last time. If I have a small Gaussian field, right, find that if I have a electric field E2 here on one side of the surface and E1 on the other side, right, then you notice that E2 minus E1 in the normal direction of the surface, let's call this M, and is perpendicular to the surface, and this has to be equal to sigma over epsilon naught, right? Okay. But it's also true, this is just from Gauss law. Recall we have another equation for electrostatic, is that the electric field, the line closed loop line integral of the electric field has to be equal to 0. Okay, so if I have a surface like this, okay, with sigma on it, right, then I can draw this. I can draw this loop. Okay, you see. Okay, suppose there's an electric field E2 here. There's an electric field E1. Okay. Then, if I look at the line integral, closed loop line integral across around C, then suppose this is all differential element, by the way, right? So I can make sure that this thickness Tmax in the limit of Tmax equals to 0. Okay. Then this line integral becomes E2 times this length here. So let's call this length dl. Along the surface, okay, minus E1, okay, if I'm going in the other direction, okay, but it will be the same DL, right? Or actually, let's start with the plus. That's called DL1 and DL2. Okay, this has to be equal to 0, right? The line integral, the perpendicular line integral values in the limit when dx goes to 0. Okay, so this left-hand side becomes just E2 in the parallel direction with the surface, okay, minus E1 in the parallel direction, right? Because I'm actually going in the other direction here, okay? Times dl is equal to 0. I can drop the dl, right? I cannot drop the dl, so that's equal to 0, but dl is finite, therefore the 2 parallel minus d1 parallel has to be equal to 0. So across the surface, whatever the charge density that you have here, right? The parallel component of the electric field has to be continuous. That's the lesson here. Okay? But the normal component has a discontinuity, right? Is this clear so far?
What do you mean by the normal?
So if on a surface, any surface you have, right, with some charge distribution, right? If I look at the component of the electric field normal with that surface, right, there is always a discontinuity that is proportional to the charge density. Right? But the component of the electric field that is actually along the surface.
Oh, along. Okay.
Along the surface, right?
Oh, that's what you meant by parallel to the surface.
I call it E parallel, right? Parallel to the
Yeah.
surface. Right? By this equation, right? Because the electric field is conservative, the closed loop line integral of E ds has to be equal to 0. Just a consequence of that shows that the parallel component of the electric field has to be the same, right? As you move across the surface.
By parallel, you mean the component like along the surface?
Yes, component along the surface.
Yeah.
Yeah. So this is
Oh, even above and below it?
yes, above and below E2, and then E1.
But are you moving it the line, or just moving it like a point, or? What do you mean?
No, I'm say if I have a surface, right? So what I draw is I draw this square, right? Let's call this square this close to square C, right? Then this line integral along that square has to sum to equal to 0, right? And I can make this thickness as thin as possible, right? Because this is differential thickness.
Yeah.
Right? Then there's only two components to the integral. One is along that line, and the other one is along this line, right? And they have to sum to equal to 0. And as a result of this, you can show that the electric field across the surface has to be the same. Right? That's the only way to guarantee that.
But in that case, it's not, or it's,
No, that's the normal component.
okay, yeah.
Right? That's perpendicular.
Yeah.
In general, along the surface, if I have a surface, right? There's an electric field here, E, right? And there's another electric field here, E. Called E2, E1. And I'm just looking at this projection. The normal projection has a discontinuity here, but the parallel projection has no discontinuity. Is that clear so far?
Why is it that you were able to go from, conclude that like the 2D parallels subtracting each other is 0? Because since you're taking a dot product, can it just be that they're perpendicular to DL, so they can Like, they could still have.
Oh yes, correct. The normal component can change across the surface.
Oh,
right.
okay.
But the parallel component cannot.
Okay.
Yes.
Okay, so you don't need to have like the vector scientific ease there.
Well, I put a parallel. Normal sign here. I will draw it with the normal direction. Okay. So just remember this one now. Okay. So how did we end last Wednesday? We found that the divergence of the electric field is equal to rho over epsilon naught, right? And also we know that the electric field is given by the gradient of potential, right? These two equations give you the Laplacian of E is equal to minus rho over epsilon naught, right? And in particular, if rho is 0, then we have this equation that we solve. Okay? So just remember this for now also. In general, this is a consequence of a Gauss law, right? You cannot have a stable configuration of charges in free space. Say, if I want to track a particle Q, right? In general, it's not possible to use electrostatic. So why is that? Because what happened is, of course, an electric field generated by the charge Q cannot act on itself, right? So this Q has an electric field, right? But it cannot act on itself. So I have to look into the effect of electric field generated by other charges on that charge Q, right? So if I look at the region in empty space, it's empty here. You might have charges elsewhere, okay? Then, if I want to stably trap a charged particle plus Q inside, right? Then you must have your electric field inward everywhere. Right? Okay. Only in this configuration you can trap plus Q inside that region. Okay. Good. If that's the case, then the line integral, so this is the electric field S plus Q that you want to put inside here, right? Then this integral ETA, okay, around the closed loop surface cannot be equal to 0, right? Okay. But Gauss's law says that it has to be equal to 1 over epsilon naught, so E, right? But there is no charges inside, right? So this has to be equal to 0. So what you have is a contradiction. Therefore, in free space, it's not possible to actually have a configuration of electric field where if you put a plus charge in there, then things. Anytime you displace the plus charge around this space, it always comes back to the center. That's not possible to do.
The first problem in the homework, which is combined motion, it's not stable equilibrium.
Very good question. I'll answer that.
Can you go over it again?
Okay. So yeah, this is kind of subtle, right? This is actually just a consequence of Gauss law. Right? There's two ways to prove this. One is that is a consequence of the Laplacian, but we can talk about that later. But simply by application of Gauss law, right? In free space, right? If I want to trap a particle, say a proton, right, in some region of space, right, that's empty, right? You might have charges elsewhere, right? In order for you to do that, then electric field in that point that you want to trap the particle has to all point inward, right? Otherwise, the proton will escape, right? If somehow you have a system that way, then the proton will escape that way, right?
So you have other charges around it?
Oh yeah, you might have other charges around here.
Oh, but
That create
yeah.
the field, right? But in the region of space that's free, right? For you to trap the particle, the electric field all has to point inward, right? So in that case, then the flux because the surface S cannot be equal to 0, right? In violation of the Gauss law. Because Gauss law says if that region of empty space has no charge, right, then this has to be equal, has to be identical to 0. Sure.
Why do you say it has to be identical? Why do you say it has no charge?
So the proton cannot act on itself, right? So let's take the proton out, right? Suppose I want to trap a proton here somewhere in free space, right? Then all the electric field coming from the rest of the universe has to be in such a way that they all point inward.
Or out.
Sorry?
Or outward.
Or outward in the case of in the other case if you want to trap an electron, say, right?
But you can have a proton and trap it by having an equal force in every direction. Away from it. That would be nice.
No, it will be, it's very big again.
Say if you had like a ring of electrons around it, and that would be forced away from the proton, but it would still be trapped there.
I don't think that counts as stable though.
Yeah, I don't know if it's stable. I'm
It's
confused
like-
about your configuration.
So-
I'm talking about just in free space,
Okay.
right? That would be, and this is relating to the question that Victor has in the homework. Because in the homework, are you referring to the homework problem? So, yes, in the homework, you did this, right? The electron shell, right? I don't know if you remember the electron shell. The field everywhere is inward. Okay? And E is given by minus rho R over the epsilon naught. Right? In the direction of that. Right? So, if I place my proton in the problem that you have 2 protons, but suppose you only have 1 proton, then this is a stable place to put it. Right? Because everywhere you go, right, you have an electric field pointing inward. Right? So isn't this a contradiction to what I just said?
Is that not free space?
Yes, it's correct. This is not free space. In free space, that's not possible to have. In free space, you can have your charges everywhere else, right? But if I just consider a volume with no charge inside, then if all the electric field is pointing inward, then you have a violation of Gauss law.
So isn't free space technically not close to surface?
Sorry?
Isn't free space not close surface?
No, if I have a free space, I can just, this is just a mathematical surface, right? It's a mathematical Gaussian surface.
So you're assuming this to be like.
So if you take out a voltage from the center of the electron jelly, does it make the whole free space?
Okay, so if you somehow make the jelly looks like this, right? Then the proton here is not a stable trap.
Is that what?
It's not a stable trap. It will if you roam around,
Oh,
right?
yeah.
You know, because the electric field is zero inside, right? I mean, there's a lot of subtlety here that I don't want to go into yet until we discuss the conductors. But the point being that even in this kind of situation, right, it's not stable. Nothing is stable electrostatically. Right? If I put a proton here and I have a minus charge here, right, this will collapse too. Right? Electrostatic is inherently unstable configuration. Right? If I have a proton, I have an electron jelly, right? You know, what's preventing the electron jelly to actually collapse into the proton? That's the thing. Okay? So, with that in mind, let's move on to the topic of inductors.
You said the electron jelly would collapse.
Yes,
Well, why can't we just have a shell?
Okay.
And when we look at a shell, the shell itself wants to propel itself. Put an opposite charge in the middle, we could keep everything inside.
Yeah, but I think you're going beyond just electrostatic configuration, right? Because you have to talk about solids and
We have a
metals.
Not for the charge, sorry.
But if it's just free charges in free space, right? It's not possible to have a stable configuration. You just prove that. Right? In any free space, it's not possible to have an electric field all pointing inward if there is no charge inside. Right? Or for that matter, outwards.
Or a cube by itself without, like a stable
Yes,
cube
unless
without.
there is a charge inside.
Yeah.
Right? If there is no charge inside.
But then it's not free space, right?
Right.
Okay.
So if you have a volume with no charge, then it's not possible to have all the electric field pointing inward.
Wait, so like throughout this, we've been talking about like stable as in like electric field pointing in at every point, but does that, like having no configurations, does that also apply to just any situation where every charge has like zero net force on it, or
I'm confused about the question. Say it again.
like, because in this case you have like all the charges are stable, so if you displace them, they go back to where they were,
Yes,
right?
yes, right.
But would that also, would the fact that there isn't any is impossible also apply to a situation where all the charges are just have zero force on them?
Yeah, sure. I mean, they might have a zero force on them, right? But so we mean like in this case here, right? You can have zero electric field everywhere inside, right? But it's not a trap,
Okay.
right? It's not a stable situation, right? A stable situation refers to a configuration where if you displace things a little bit, it will always come back.
Oh.
Yeah. Okay.
So is the electric field like only comes about when there's charges around, right?
Yes. Yes.
Is it
Suppose I can-
there without charges? Is that what this is saying?
No, meaning that, very good question, meaning that if I just look at a region of space where there is no charge, right, but you might still have electric field, right, coming from configuration of charges elsewhere,
Right.
right, so there might be electric field on the wall, I mean, coming from charges on the wall, right, if I just look at a volume here, right, it's not possible to have all the electric field pointing inward,
Oh, okay.
right,
Yeah, there's nothing to make it
because
come.
there is no charges,
Yeah.
because it would be a violation of Gaussian. If that would be the case, then you would have a violation of Gauss law. Okay? So I don't know, but this is only referring to electrostatic, right? I mean, you probably heard about ion trap, right? I mean, it's in the news, right? It's possible to trap ion, right? So how is that possible? It's only possible because the potential that's doing the trapping is actually time dependent. Electrostatically, it's impossible. Okay. So, with that in mind, let's move on. Things are stable, not because of electrostatic, but because quantum mechanics is involved, right? And what you have in most materials, right? You have a perfect balance of plus and minuses. Okay? And since, as you already know from the first lecture, right, the electrical force is actually much stronger than, say, gravity, right? And then you remember this, this is like 10⁻⁹, much stronger than the forces of gravity, right? Then it's almost impossible to disturb that balance, right? Okay, and the best you can do. If you say rub plastic and glass together or fur, right, is to transfer electron very minute amount of electron here and there, to display some things a little bit here and there, right? That's one way to do it. Right? But in general, it's not almost impossible to move charges by a large amount, right? So if what you have then is an insulator. Another possibility is inductor. In inductor, say metal, for example, right? A fraction of the charge is free to move. Doesn't require much, right? Say, a block of metal has 10 different atoms, right? Just one more, right? Only a small fraction give you a lot of forces already. And in a conductor, in a what we call a perfect conductor, we consider a situation where charge can move freely inside. Okay, and it's actually an electron that can move freely. Okay? Fractions of the electron. Okay? So it's possible to polarize this, right? So if I have a neutral piece of metal, okay, it's possible to pull all the electrons to one side, right, leaving you with positive charges over here. Okay. And it's also possible, if I want, I can also inject charges. I can add plus charges into the metal, and it will also move around freely. Right? Also electron. If I move the electron, I mean, mostly, of course, you have to move electron, right? You cannot move positive charges. I can move the electron into the metal, and it will have to move freely inside. Okay? So what happened inside metal, inside the conductor, because charges is free to move, right? Charges can move freely. Then the electric field inside has to be equal to 0. have a field inside, then charge will move, right? Without any barrier. Okay? So inside the conductor, there can be no charge. The net charge has to be equal to 0. Okay? Because anytime you establish an electric field inside, charge will move in such a way to cancel that electric field. It's not quite obvious, and this in the end you have to solve it. But it's generally true that what happened inside the conductor, there is no charge. If you have charge, they have to reside. Charges has to reside on surface. We cannot leave the surface. Okay. And what other consequences do we have on this? And since we know that since electric field is equal to minus the gradient of potential, then the potential inside the conductor has to be constant. Okay. And it's equal to the potential at surface. Okay. So anywhere on a conductor, along the surface of a conductor, is a potential. Okay. Otherwise, if you don't, right, you establish a potential difference between these 2 points on the surface of the conductor, then you establish an electric field. Anytime you have electric field, then charges will move, right? And charges will move in such a way to cancel that field. Okay. Any questions so far? Yes.
So, do you not to take into account whatever forces are keeping the charges like on inside the conductor? Because otherwise the charges would like if you had all positive charges, they would just fly apart, right? Like there's something keeping them.
Yes,
in the conductor.
correct.
Just ignore that, or what?
So we'll just ignore that for now because that's a consideration that comes from quantum mechanics, right?
Oh.
Right. So you have to actually establish the stability of solid, right? As we said earlier, right? Any electrostatic configuration is inherently unstable, right? It will always collapse, right? And then we neutralize everything, right? Plus and minuses eventually get on top of one another, right? And the reason they don't is actually it's outside of electrostatic. So same case in the case of conductor too, right? You have a perfect balance of plus and minuses, right? But a fraction of the electron, and this is also coming from quantum mechanics, is actually free inside, only a small fraction, right? But that's still a lot because you have 10 to 20 atoms inside the say like a small little block of solid, right? So only a small fraction of this is a lot of electron, and they can move freely across the conductor in response to electric field from the outside. Right? But yeah, we're not worrying about the part where what makes the solid stable. Okay. So where are we? So just remember this, right? Electric field, the charges inside the conductor is 0. If you have any charges, it has to reside on the outside. The electric field inside has to be 0, and the potential has to be constant. Okay. So if I have a conductor of any shape, right? Then recall that E2 normal has to be equal to sigma over epsilon naught. E2 parallel is equal to 0. Right? So on the conductor at the surface, the electric field has to be known. Because you cannot have a parallel component on the electric field. What happens is I can just draw another one of this loop, okay, right? And then I can show that this has to be equal to 0, right? Along this loop, right? But we know that E1 is inside, right? This is E1 is here, and this is E2, right? E1 has to be 0 anywhere inside the conductor, right? Therefore, E2 has to be equal to 0 also. Okay?
Just to be clear, that conductor is a conductor with excess charge.
And excess or neutral.
But if it's neutral, that and all the charges on the outside should be net positive charge inside.
Yeah, well, you can always polarize it, right? So, you can have negative here and say positive here. Right? The net can still be neutral. I have a jet. So far, the discussion is completely general, right? The conductor can be charged or no charge. Right? And this is always true. Right? On the inside, the charge has to be equal to 0. Whatever residual charge you have has to be on the outside, on the surface of the conductor.
And then what did you mean by the potential? Like, is that if you have a charge, then it needs to be constant? The
Charge or
potential?
no charge?
Charge or no charge?
Yeah, charge or no charge, it has to be constant.
Okay. And then is it equal to at the surface or same as with the?
Yes,
Okay.
right. So basically, on a conductor, the everywhere in the conductor is a constant potential.
Mhm.
Right? So everywhere, which is like everywhere, in or on conductor, it is constant.
If you can have negative charge and positive charges all on the outside, then why is it separate? Why does everything go to the outside?
Suppose I have a plus Q here, right? Because the conductor is infinitely polarizable, right? Charges can move freely, right? Then all the electrons will get attracted to the plus charge, right? And it will stop at the surface.
What if there is no plus Q?
If there's no plus Q, then yeah, then it's neutral, right? Meaning that there can be other electric fields everywhere generated externally somehow, right? I mean, I can put a piece of metal inside an electric field, right? So I can have an electric field somehow, like that, right? Then what happens is inside this conductor, right? The minus charges will migrate to this side, right? Because they get attracted by because it has a Coulomb force going that direction. Right? So you have a minus charge, and then they have to stop at the surface, right? And because the conductor is neutral, that leaves you with positive charges everywhere else. Right? But the charges inside has to be equal to 0. Okay. So all we established just from the fact that electric field is conservative, right? That the parallel component of the electric field across a conductor has to be equal to 0. Okay. But the normal component of the electric field into normal is equal to sigma over epsilon naught, right? Okay, but this part is 0 because this is inside, right? So just right outside of the conductor, the electric field is just sigma over epsilon naught. So everywhere on the conductor, right at the surface, the electric field is normal. Or it can be pointing inward. I mean, when I make things point inward, it doesn't mean that there is electric field inside, right? It can point inward like that. Okay. It's always normal. Okay. And the magnitude is proportional to the surface charge density at that point. So that's all there is to it, right? As far as just the physics of conductors. So let's look at an example. Before I do an example, let's look into this manipulation. Let's look into a cavity. Suppose I have a conductor with a hole in the middle. Right? So this is the conductor. Okay. What's the electric field inside? That's the question. Okay. So we know that the potential is the same everywhere. E is constant. Everywhere. Right? So in particular, along the inner surface, let's call this S, right? Along inside S, on surface S, the potential is constant. So there is two ways to actually show this. I'm not going to follow Purcell. Purcell has one solution, but inside here, if there's an electric field, right, it cannot close onto itself, right? If I have an electric field, it cannot do this, right? Because what happens if I have something like that, if this is my electric field, then this is not equal to 0. Okay? Field lines cannot close onto itself inside this inside anywhere in this space. Okay? So if there is a field, if there is an electric field inside the cavity, right, then it has to go, then it has to start somewhere on the surface, and it has to end somewhere else along the surface. Right? Okay. Amen. Sorry? Oh, yes. So my first argument is this. If there is an electric field inside the cavity, right? Field inside, it cannot form a closed loop. Right? It cannot, the field line cannot close onto itself because it will violate that equation. Right? Okay. So this doesn't work, right? So if there is an electric field inside, then it has to start at the surface, right? And it has to end at some other point on the surface, right? Let's call this curve C, right? Now, what I do is that I can close the loop here, right? Let's call this whole loop C, right? C, okay? Then this integral along the closed loop, E, EL, along C, right, has to be equal to 0. Right? Okay? But there is no electric field inside here. Right? Because inside the conductor, right? So this portion, let's call this portion C1 and the rest C2, right? This portion along C1 of the L is 0. Right? Okay, because the other part is already identically 0. Right? Therefore, this electric field, there cannot be any electric field in here. Because this line, if I'm following the field line here, right? Just following the field lines, then this part has to be positive. Right? But the argument of the conservative of the electric field, because of that, because of this, right? Then this portion of the line integrity has to be equal to 0 too. Right? So therefore, there cannot be any electric field inside the cavity.
Cavity is a hole inside.
It's a hole inside the conductor, right? Yes, right. So the lesson to take home here, this is called there's a name for this. It's a Faraday cage, right? Have you seen somewhere where they can sit inside a chicken coop or something, from copper, and they can do all sort of things on the outside with nothing inside. So this is exactly what happened. Right? If I have a cavity, a conductor with a cavity, right? And I can put charges anywhere I want, right? And I can sit inside. Nothing, you will feel nothing. The electric field inside has to be 0.
But all you prove is that the potential difference between any two endpoints of the inside is the left-hand.
No, but there is a, very good point, but I have two arguments here, right? I'm just saying that if there's an electric field in here, it cannot loop onto itself, right? If it loop onto itself, it will not satisfy this equation, right? The curl of the electric field has to be equal to 0, right? We'll talk about that later on, right? But if it cannot loop onto itself, then it has to start somewhere and end somewhere else, right? And then my second part of my argument holds, right? So therefore, the electric field inside has to be equal to 0. Sorry, guys, that's the end of the hour. We'll continue Friday.